Hi y'all, this is section 3.3 and today we'll be learning how to graph the derivative of the function if we're given a graph of the original function. Okay, so we need to make sure we have this vocabulary down. These are going to be things that we're going to be using throughout the entire year, and we want to make sure we know how the derivative relates to whether the function was increasing or decreasing. Okay, so big idea, remember that derivative is the instantaneous rate of change. How fast is a function changing at a given moment? Okay, so if the function is increasing at a certain point, then we know that the derivative will be positive. If the function is decreasing at a certain point, we know that the derivative would be negative. Okay, if the function has a nice smooth minimum or maximum, okay, when I say smooth, I'm meaning some sort of like nice parabola, or something that you don't have an abrupt change in direction. It's continuing on, and we'll be modeling this with like taking a ruler and drawing in the tangent lines. We could go like this and like this and like this, and our tangent lines would be approaching the same value as we approach from the right and as we approach from the left. It'd be getting closer and closer to that flat horizontal line. Okay, so we would say that the tangent line at those kinds of points are 0, and those are actually really important points. We'll be starting with those points when we go to graph. Okay, and then big idea here is that the function has a discontinuity, so the function is discontinuous. You know for sure that there's not going to be a derivative at that point. And if there's a cusp on the original function, you know that the derivative will be undefined at that point. Okay, so let's go ahead and just jump in and start looking at one of these examples. So looks like we have a nice cubic function here. Notice that we do not know what the equation is. Okay, and our goal is to sketch f of x, or f prime of x. We want to know what the derivative graph would look like if this is our original. Okay, so what I'd like you to do is think about wherever the function is increasing. So here we can see increasing, 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 increasing. So from here, it looks like about -8, all the way through to, looks to be -4. See that the function was increasing. Since the function was increasing, we know the derivative will be positive over that interval. And realize positive will mean above the x-axis. Okay. From this point here to this point here, the function is decreasing. So I know that my derivative will be negative or below the x-axis. And then from this point on, the derivative function was increasing, so I know my derivative will be positive. Okay. So what I like to do on problems like this is to, especially as I'm first starting off, is to give myself a table of values and imagine if x is a certain coordinate, what the output was at that point. So what is f of x? And then let's think about what the slope is at that point. And eventually what you're going to be doing is graphing at this x coordinate what was the derivative at that point. So f of x is already sketched for you here. We already know what that guy looks like. We're going to be drawing what f prime of x looks like. Okay. So here, let's use the minimums and maximums first. That's what I always suggest that you start with. So here we have a nice maximum, and that looks to be occurring at -4. So if I use -4 for my x coordinate, okay, remember tangent lines, if you were to draw on the tangent line along this curve, so it's right here at this point, looks something along these lines, pretty steep. If I was at this point, not quite as steep. So as we move into this point, hopefully you can see it's getting less steep, less steep, less steep. So if we drew in the tangent line right at that point, we would have a nice horizontal line. And we know that the slope of horizontal lines are 0. So at -4, we have a slope of 0. Okay. Now the output looks to be 10. So if I wanted to fill that in, it looks like my point is -4, 10, but the slope at that point would be 0. Decreasing along this interval, and then here again, at this point here, if we looked at the tangent line, so if we were to draw that in as we get closer and closer, our tangent would be horizontal. So at this point here, which looks to be at 2, we know the slope of that tangent line right there would be 0. Okay. So those are two really important points. And that's actually where you're going to want to start when you go to sketch. So just based on that right now, if I do a rough sketch here of x and f prime of x, I know at -4, I have 0. Boom. And at 2, I have 0. Boom. Okay. Now, big idea. Remember, to the left of -4, so over this whole interval, as you read it from left to right, you can see that this function is increasing. So because the function was increasing, I know my derivative should be positive. Okay, and let's just grab one value over here. In my sample, let's see, I'd used this point right here. So I plugged in -7. So -5, -6, -7. So right here at -7, I look to be right around here. Okay, and if I plugged in -7 into, or if I looked at the slope of the tangent line, okay, so I'm going to try and draw in a line that goes right with the curve, but is, oh, that did not work at all. My bad. Let's try that again. So I just have to pretend that I'm using the ruler, but I can't actually use the ruler. Y'all can use your ruler. So I pretend that I'm using the ruler, and then I just draw it in. Okay, that was not perfect, but tangent lines, remember, you're trying not to have it go through the curve. You just want it to lie right next to the curve and only go through it at that one single point. So I'm going through it a lot up here, so I was clearly a little bit too far this way. But the main idea is that that is clearly a positive slope. That line is going up, and it's pretty large. So if I was to think about the rate of change from this point to, let's say, that point, I'm going up 1, 2, 3, 4, 5, 6, 7. It looks like I'm going over, 1 or 2. So let's just say I was going up 7 and to the right. Let's say I was going up 1, 2, 3, 4, 5, 6 and to the right 2. So if I was going up 6 to the right 2, so up 6 to the right 2 would mean my slope is somewhere around a +3. That's not exact by any means, but it's good to give yourself a rough estimate. Okay, so if you draw on the tangent line and then literally just calculate or estimate the slope of the tangent line at that point, that'll give you a pretty good approximation. So at -7, I was at 3. So that was -4, -5, -6, -7. I'm up somewhere here at 3-ish. Okay. Now, if I choose a point, let's erase this guy. I know you guys can't erase yours. But let's choose a point closer to that peak. So let's go right in here at -5. So at -5, I'm at this point right here. So if I was to draw in my tangent line, somewhere like, zoom, looks actually a little too steep. Let me redo that. So if I was to go, it's like right around in here-ish. I don't know, somewhere in that range. So I was going to take that point and maybe, let's say that point right there.
Good afternoon, Carmel students. Just an update. The PSAT
Sorry
tests
for the
have all
interruption.
been sold out. There are no more available. Once again, the PSAT tests have all been sold out. Thank you very much and have a good day.
So at -5, y'all, it looks to be like I'm going down 2 and to the right 2. Down 2 and to the right 2-ish. So I know it's not exact, but if you were going down 2 and to the right 2 or up 2 and to the right 2, basically you have a slope somewhere in here, like 1. And maybe it's slightly more or slightly less, but you get the rough idea. And so if you're over here at -5, you'd be up here at 1. Okay? This is the hardest part for students to figure out. The function is increasing, okay, so I know my derivative is positive, which means I know my derivative will be above the x-axis to the left of that 0. So I don't know exactly how these dots get connected, but I do know that to the left of this 0, because that function was increasing the entire time, I know I'm going to be above the x-axis that entire time. So I'm just going to go ahead and guess. It looks maybe something along those lines. Okay. Now from this peak to that minimum, I am decreasing the entire time. So because my function is decreasing, I know my derivative should be negative. So I know I should be below the x-axis the entire time along my f' graph. So let's grab a point and just estimate the tangent line in there. So, I don't know which one looks good. Let's see, let's take that y-intercept. We're going to draw on the tangent line there. You're trying to get as close to the curve as possible, but try to have it only cross through or touch at that one point. So, zoom, something along those lines. Now I know it would actually cross through up there, and that's okay. We're talking about in this neighborhood, it should only touch once. So if we estimated that rate of change, let's say that dot to, how about that dot? So it's going down 1, 2, 3, 4, 5, and to the right 3. 1, 2, 3. So, and that was at 0. So at 0, what did I say? Going down 1, 2, 3, 4, 5. So down 5, and to the right 3. So remember, traveling down will get you the negative. So it's about negative, 5/3, about -2-ish. again, it's not exact, but it's an approximation. So we can say here at 0, the rate of change would be about a -2. So here at 0, I want a rate of change of about -2. Okay? And what I want you to connect is that as you move from that peak to that minimum, if you were to draw in your tangent lines, these would be getting, it would get steeper and steeper for a while, and then it would start to get less steep and less steep as we got closer and closer to that minimum. Okay? So realize our slope is 0 here. As we move, it's getting away from 0 in a negative direction, and then it's coming back to 0 in the negative direction. Okay, so because this function was decreasing that entire time, I know that from these 2 points, my function needs, or my derivative needs to be below the x-axis that entire time. They all need to be negative. So I don't know exactly how these dots get connected, but I do know that they get connected. Okay? And then after that, the function is increasing the entire time, so I know that my derivative should be positive or above the x-axis the entire time. Okay, so when I drew in these tangent lines over here at something positive, like right in here, if I drew in that tangent line, looks something along those lines. Okay, and the slope of that line, if I estimated that, looks like I'm moving up 1, 2, 3, 4 to the right 2. So up 4 to the right 2 would give me, so up 4 to the right 2 would give me about 2. And that was when x was 1, 2, 3, 4 was my x coordinate. So over at 4, my derivative should be 2, somewhere in there. 1, 2, 3, 4. Wait, 1, 2, 3, 4. 1, 2. Okay. So right now, especially as you're first starting, I actually don't care as much about the shape that your derivative graph takes. It's more about whether you're above or below the x-axis in the proper places. Okay. So you know you're going to be above the x-axis over here because the function was increasing, and therefore derivative would be positive. Okay. So I don't know if you see this rough sketch here, but it kind of looks parabolic. And in fact, it actually is parabolic. If this was a cubic function, this should actually be a parabola, and we'll learn the shortcut next week. But the power rule will tell us that if we're taking the derivative of a polynomial function, our derivative will always be 1 power less than what we started with. Okay? So if we had done this perfectly, this should be a perfect parabola. I can see over here it was a little weird, but it actually is a parabola. Okay? So I know that was really long, but what I'd like you to do is, and if you've drawn on this, go ahead and just re-sketch again. Basic idea, you don't have to get all the details in there. But this is what I want you to eventually be able to do with these problems. Is, all right, if I want to sketch f prime of x, I will start with my zeros. So right here, I would put a 0. Okay, boom. And right here, at my minimum, I would put a 0. Boom. So those 2 zeros right there are those 2 zeros right there. Okay, those should line up perfectly with my maximums and my minimums. Okay. Function was increasing over this interval. I know I should be above the x-axis for my derivative. So I don't know exactly where, but I know I'm going to be above the x-axis. And I know that might feel funny because this function is increasing, but my derivative goes down because the rate of change is getting smaller and smaller as you go up. Okay, so the rate of change should be getting lower, closer and closer to the x-axis. In here, function's decreasing, derivative negative. I know these 2 dots are going to get connected, so it must look something along those lines. And then here, function increasing, so I'm going up. Okay. For all the rest of the examples, I'm not going to do all of this work here. I'm going to jump right into this guy. Okay. Please always make sure you label which one's your derivative and which one's your original. If you put them both on the same picture, that's eventually what I want you to be able to do, make sure you're labeling them in some way so that we all know which one's the original and which one's the derivative. All right, y'all, let's see if I can get through this before lunch ends. Okay, so example number 2, every maximum and minimum, we know that the rate of change there would be a nice horizontal. So for here, that would be a 0. The rate of change right here would be a 0. The rate of change right here would be a 0. The rate of change right here would be a 0. The rate of change right here would be a 0. The rate of change right here would be a 0. Okay? If you can start with that, you'll have a much better idea of what the big picture is going to look like. Okay? So we know that this is a nice continuous function, so our derivative should also be continuous. There's a nice smooth curve, so we're not going to have any discontinuities here. Okay? So think about this. If the function is decreasing over this interval, I know that my derivative should be negative over that interval. So I know connecting these two zeros, I'm going to be somewhere in the negative range. If my function is increasing, then I know I'm going to be above the x-axis, and they have to get connected. Function decreasing, below the x-axis for derivative. Function increasing, above the x-axis for derivative. Function decreasing, that meant that the derivative must have been negative, therefore your value would be below the x-axis. Okay? This is kind of getting us ready for one of the rules that we're going to be learning. This might look kind of sinusoidal, and we'll be learning the rules of what the derivative of sine is and what the derivative of cosine is. Okay? So I don't care how high or how low these peaks are. Those zeros need to be in those spots, and then you need to be above and below the x-axis on those intervals. So there's our f prime, if that was our original f. Now we're going to get a little tricky. Okay? Notice here we have a line, and hopefully remember that the rate of change of a line is staying constant. So we can just refer to the derivative of the line as the slope of that line. Okay? So if you look at this carefully, it looks like I'm going up one to the right one, up one to the right one, up one to the right one. So for every single value from here to here, I know that the slope at that point would be 1. The slope at that point would be 1. The slope at that point would be 1. So it's going to be 1 until we get to this point here. Okay? I should have probably been consistent, and let's start with these nice smooth minimums. So right here, I know that my rate of change would have been 0. So my rate of change would be 0. Okay? Now this guy is not a nice smooth maximum. He is a maximum, okay? But we're going to figure this out yet, and I don't know if I'm supposed to teach you in this section or not, but I'll go ahead and teach it to you. That, oh yeah, I did already in the first slide. That at a cusp, the derivative will not be defined. As you come into the right of that cusp, so you're here at that 0, and then if we wrote in the tangent line like right here, that'd be a pretty steep negative. Okay, right there, right before the cusp, would be also a pretty steep negative. But as we approach from the left, we are just at that constant 1 slope. So right at that point, we don't know how to draw on the tangent line at a cusp. If I try to draw on the tangent line there, I could draw that, I could draw that, I could draw that. There would not be a unique tangent line that only touched that point at one point. So we say we cannot take the derivative. Okay. So if you have a cusp, you know the derivative will be undefined there. So you'll show that with an open circle. So slope 1, 1, 1, 1. So slope 1, 1, 1, 1. But at this point, we do not have a defined derivative. So we have to throw an open circle there. Now in here, this would be pretty steep in the negative direction. Okay, so the function's decreasing. I know my derivative should be negative below the x-axis. I don't know exactly how steep, but I know it's somewhere negative. And then as we move here, we're getting closer and closer to 0. So it would be somehow connected through like this. After this point, the function is starting to increase and get larger and larger, so I know it would be going up and up and up. Okay. So I don't know exactly how this graph would look like, but I know that this guy here, so this zoom, and then zoom, would be something along my lines for my f prime graph. Okay. I know this is only day 1, so it might still seem really challenging, and if you're frustrated, try not to get frustrated. We'll work through it eventually. Okay. So here we have a really crazy graph. We have a discontinuity. So again, if your function is discontinuous at a point, your derivative will also be discontinuous at that point, for sure. Okay. So here I have a nice smooth minimum, so I know the derivative right there would equal 0. Boom. Okay. Not a smooth minimum, so not a 0. Not a smooth minimum, so not a 0. Okay. But we do have a nice smooth maximum right there, so that guy would be a 0. Okay. Now from here, function's decreasing. Decreasing, I know I'd have a negative derivative, so I'm going to be below the x-axis somewhere. Okay. Function's increasing, but then somewhere right around in here it looks to start to be linear. So it looks like I'm increasing, but then right around in here, it looks like it just starts to be linear. And again, it's changing at that rate of like 1. So maybe I'm starting to come up here, but then right around in here it looks like I'm jumping right to 1 the entire time. And then right here I know my derivative is not defined, so I have to show that with an obnoxiously big hole. And then to the right of that discontinuity, it still looks like it's a rate of change of 1, 1, 1. So we're going to 1 all the way into that peak. But at that peak, we do not have a derivative, so there'll be an open hole. Okay. After that peak, we have a rate of change that's negative, and it's staying pretty consistent. It looks like from that dot to that dot, I'm going down 1, 2, 3, 4 to the right 2. So down 2 to the right 1, so negative 2. So I know, starting at this point, I should have a slope of negative 2. But again, at that point, it will not be defined. So you have an open circle. negative 2, open circle, and negative 2, negative 2, negative 2 all the way into this point, so negative 2, negative 2, negative 2. That point would not be defined, so we have an open circle there. Now here, if you have a horizontal line, the slope of that horizontal line is 0. So from here to here, you just have a slope of 0, but you cannot define those endpoints. So you'd have open circles there. Function increasing, derivative positive, so I know I'm above the x-axis. Function decreasing, derivative negative, I know I'm below the x-axis. So I don't know exactly what this rate of change is here, but it's going to be something along these lines. I know it's probably pretty tricky, but bell's about to ring for lunch and I'm going to stop. Good luck, and I'll see you guys on Tuesday.